Definition of invertible functions. Hello everyone. To begin, let's look back at what we have already covered. In our previous sections, we explored the process of function composition, where we learned how to combine two different functions to create a brand new one. Now that we understand how to chain functions together, we are going to explore the opposite idea, the concept of reversing a function. To put this simply, in mathematics, if a function performs a specific operation on an input, an invertible function is one that can effectively undo that operation. This allows us to move backward from the result and return exactly to our original starting point. In the coming slides, we will look at the formal definitions and the specific conditions required for a function to be truly reversible. The concept of the identity function. Now that we have introduced the idea of reversing a function, we need to establish a foundational concept. Before we can formally define what an invertible function is, we must first understand the identity function. In simple terms, an identity function is a function that returns the exact same value that was used as its input. You can think of it as a function that does nothing to the element it acts upon. It simply leaves it unchanged. Let us look at the formal mathematical definition. A function, denoted as capital I sub x, mapping from set x to set x, is called the identity function on set x if the function I sub x of x equals x for every x in set x. To make this more concrete, let us consider an example. Suppose we have a set x consisting of the elements 1, 2, and 3. The identity function I sub x would simply map 1 to 1, 2 to 2, and 3 to 3. Understanding this concept is essential because, as we will see in the next slide, the very definition of an invertible function relies on the ability to return a value to its original state, essentially returning it to the identity. What is an invertible function? Now that we have a clear understanding of the identity function from the previous slide, let us move on to the core definition of an invertible function. First, we say that a function f, which maps set x to set y, is considered invertible if there exists another function g, mapping set y back to set x, such that the composition of these two functions results in the identity function for both sets. To put this into formal mathematical terms, for f to be invertible, there must be a function g such that the composition of g and f of x equals the identity function of x of x for all x in set x. And similarly, the composition of f and g of y equals the identity function of y for all y in set y. In simpler terms, this means that if you apply function f and then apply function g, you should be brought right back to your original starting value, x conversely. If you apply g first and then apply f, you should return to your original value, y. If such a function g exists, we give it a special name. We call g the inverse of f, and we denote it as f inverse. Consequently, our conditions can be rewritten using this notation. F inverse composed with f equals the identity function of x, and f composed with f inverse equals the identity function of y. In the next slide, I will use a real-world analogy involving secret codes to help you visualize how this undoing process works in practice. Real-world analogy, the secret code. Now that we have covered the formal definition of invertible functions and the identity function, let's move on to a real-world analogy to make these concepts more intuitive. To understand invertibility, consider the process of encoding and decoding a secret message. First, let's look at step 1. The encoding function, which we will call f. Imagine you have a simple rule to encode a letter by shifting it one position forward in the alphabet. For example, if your input is the letter A, the output is B. If your input is B, the output is C. In this case, f is our encoding function. Next, in step 2, we need a way to get the original message back. This requires a decoding function, which we will call g to reverse the previous operation. The rule here is to shift the letter one position backward. So, if the input is B, the output is A, and if the input is C, the output is b here, g serves as our decoding function. Now, in step 3, let's verify the invertibility by applying the conditions we discussed in the previous slide. If you take the letter A, encode it to get B, and then decode that B, you arrive back at the original letter A in mathematical terms. This is the composition of G and F applied to A, which equals A. Similarly, if you start with the letter B, decode it to get A, and then encode that A, you return to the original letter B. This represents the composition of F and G applied to B, which equals B. Since the process can be perfectly reversed in both directions, we can conclude that the encoding function F is invertible, and the decoding function G is its inverse, denoted as F inverse. Having seen how this works with a secret code, we will now apply this same logic to a mathematical equation in the next slide. Mathematical example. Now that we have explored the conceptual side of invertibility through the secret code analogy, let us apply these ideas to a concrete algebraic example to see how the mathematics works in practice. Consider a function f mapping the set of real numbers to the set of real numbers defined by the rule f of x equals x plus 5. Step 1 is to identify the operation. By looking at the equation, we can see that the function f takes any input x and simply adds 5 to it. In step 2, we need to find a second function, which we will call g, that undoes this operation. Just as we shifted letters backward in our secret code example, to undo the addition of 5, we must subtract 5. Therefore, we define our candidate for the inverse function as g of y equals y minus 5. Now, we must formally verify if this function g actually satisfies the conditions of an invertible function. Step 3 is to verify the first condition, that the composition of g and f of x equals x. Starting with the composition, g circle f of x is the same as saying g of f of x. When we substitute the definition of f, this becomes g of x plus 5. Since the rule for g is to subtract 5 from whatever is inside the parentheses, we get x plus 5 minus 5. This simplifies perfectly to x, as we learned in our discussion on the identity function. This result confirms that the composition results in the identity function for the first set. Step 4 is to verify the second condition, that the composition of f and g of y equals y. Following the same logic, f circle g of y is written as f of g of y. Substituting the definition of g, we get f of y minus 5. Since the rule for f is to add 5, we have y minus 5 plus 5. This simplifies to y. This confirms that we have also achieved the identity function for the second set. In conclusion, since both composition conditions are satisfied, we have mathematically proven that the function f of x equals x plus 5 is indeed an invertible function. We can now officially denote its inverse as f inverse of x, which equals x minus 5. Keep this process in mind, as in the next slide, we will discuss some common pitfalls, such as the difference between a function's inverse and its reciprocal. Common mistakes to avoid. Now that we have seen a practical algebraic example of how to find an inverse, it is important to address some common pitfalls. Let's look at the most frequent mistakes students make when dealing with invertible functions. First, let's discuss a very common point of confusion regarding notation. In your previous algebra courses, you learned that x to the power of -1 is the same as 1 over x, which is the reciprocal. However, in the context of functions, f inverse does not mean 1 over f of x. It is crucial to remember that the superscript -1 here refers to the inverse mapping, the undoing process we just practiced, and not the multiplicative inverse. Secondly, you must be careful not to assume that every function is invertible. In reality, not all functions have an inverse. For a function to be invertible, it must be a bijection, which means it must be both one-to-one and onto. To explain this simply, if a function maps two different inputs to the same output, for example, the function f of x equals x squared, you cannot uniquely go back to the original starting point. If the output is 4, you wouldn't know if the original input was 2 or -2. Because there is no single, clear path back, such a function is not invertible. Finally, do not ignore the domain and codomain. As we saw in our secret code analogy, the inverse function essentially reverses the direction of the mapping. If the original function, f maps elements from set x to set y, then the inverse function, f inverse, must map elements from set y back to set x. The starting point of the original function becomes the destination of the inverse. Keep these warnings in mind as we move to our final slide to summarize the key takeaways of this lesson. Key takeaways. To wrap up our lesson on invertible functions, let's go through the key takeaways to ensure everything is clear. First, let's recall the identity function. As we discussed at the beginning, this is a function denoted as I of x equals x, which simply leaves the input unchanged. Whatever you put in is exactly what you get out. Next, we have the definition of an invertible function. A function f is said to be invertible if there exists another function g that can effectively undo the operation of f when we compose these two functions in any order. The result must be the identity function. In terms of notation, we represent the inverse of function f as f inverse. Please keep in mind the warning from our previous slide. This notation refers specifically to the inverse mapping and should not be confused with the algebraic reciprocal. Finally, let's review the core requirement for invertibility. For a function to be officially invertible, two conditions must be satisfied. First, the composition of f inverse circle f must equal the identity function of x, and second, the composition of f circle f inverse must equal the identity function of y. Both of these must be true to guarantee that the function can be reversed regardless of which set you start from.